Welcome to The Explainer. Today, we're going on a hunt for a hidden mathematical pattern, a single, elegant idea that secretly connects some of the most complex areas of computer science and, believe it or not, helps us solve problems that seem completely impossible.
Okay, so what are we even talking about here? Let's look at a collection of some seriously heavy-hitting fields from logic and computer science. We're talking about formal verification, temporal logic, automata theory, even the mu calculus. I mean, these are the theoretical engines that power modern computing.
At first glance, right, they seem totally disconnected. What could the logic of time possibly have to do with the structure of graphs? But, as we're about to find out, there's a powerful, hidden mathematical principle that actually unites them all. It's a fundamental idea about order and about infinity. And the hero of our story, the concept that connects everything, is an abstract but incredibly powerful idea called a well-quasi-order, or WQO for short. And its superpower? Well, it's taming infinity. So what exactly is a WQO, really? In plain English, it's a special kind of ordering that prevents infinite, incomparable chaos. Imagine you have a bag with an infinite number of items. A WQO is a guarantee that if you just keep pulling items out, one after another, you can't go on forever without eventually finding a pair where the first one is, in some way, smaller than or equal to the second one. That guaranteed ascending pair is everything. So how does it do this? Well, a WQO basically stands on two pillars. The first one, no infinite descending chains, is pretty intuitive. It just means you can't keep finding smaller and smaller and smaller things forever. But the second one, no infinite anti-chains, that's where the real magic happens. This means you can't have an infinite collection of things where none of them are comparable to any other. It's like saying you have an infinite set of Russian nesting dolls. It's impossible that not a single one of them fits inside any of the others. Sooner or later, you're guaranteed to find a pair where one fits inside the other. Okay. I know this might still feel a little up in the clouds, so let's bring it right down to earth. We're going to look at two landmark theorems that really show the power of WQOs in action. First up is Higman's lemma, which goes all the way back to 1952. And it applies this massive idea to something we use every day, words, or, strings of characters. It says that if you order strings by whether one is a subsequence of another, then congratulations, you've just created a well-quasi-order. So what does subsequence even mean? It's pretty simple. Take the word computer. The string CPTR is a subsequence because you can find all those letters, C, P, T, R, inside computer in the right order, even if you have to skip other letters to get there. And here's the mind-blowing part that Higman's lemma proves. You literally cannot create an infinite list of words where no word is a subsequence of another. Eventually, one has to fit inside another. It's a mathematical guarantee. Then, fast forward to 1960, and a guy named Joseph Kruskal takes this whole idea and just blows it up. His tree theorem applies the exact same WQO principle, but not to simple, flat strings. He applies it to these much more complicated, branching things, trees. The ordering for trees is called topological embedding. You can think of it as basically the tree version of a subsequence. A smaller tree embeds in a larger one if you can find its basic shape in there, maybe by snipping off a few branches. And just like with strings, Kruskal proved you can't have an infinite sequence of trees where none embeds into a later one. That fundamental rule against infinite chaos, it still holds, even for these complex structures. And this is really the key takeaway here. This wasn't some isolated, one-off discovery. As Kruskal himself said a few years later, this is a frequently discovered concept. It was a pattern that just kept showing up again and again in different fields, which was a huge sign that something really deep and important was going on. Okay, so now let's bring it all home. We need to connect these dots and get back to our original mystery. How does all this abstract math about strings and trees actually help us in the real world of computer science? Yeah, this is the big one, right? How do these ordered strings and trees help us prove that a piece of complex software actually works the way it's supposed to? It seems like a huge jump, but the logic is surprisingly clean and really elegant. So here's how it works. Imagine you're trying to find a bug in a program. You can think of this as a search through a massive, maybe even infinite number of different states the program could be in. Now, we can represent these states as strings or trees. And because of the WQO principle, We know that any endless path through those states has to contain that ascending pair, that repeating pattern somewhere. And that gives us the ultimate guarantee. Our search for a bug won't just run on forever, it has to stop. And that's absolutely crucial for making automated tools that actually work.
And believe me, this isn't just some theory, it's used in practice. A great example is the model mu calculus. I know, it sounds intense, but it's a super powerful logic used to verify really complex hardware and software. And the research is clear. WQOs are a key tool used to prove that it works, specifically by establishing something called the finite model property, which is the foundation that makes automated verification possible.
So let's just step back. Why does any of this matter? Well, it's because WQOs give us certainty. They're the mathematical proof that our bug hunting algorithms will eventually stop. That certainty is what allows us to automate the whole process, to build tools that can tirelessly check our systems for flaws. Basically, they let us use finite computable methods to solve problems that seem infinitely complex. That's the real magic here. All right, so let's pull all these threads together. We started out with this list of fields that seemed totally separate, but now we've seen how this one powerful idea really does act as a unifying principle. So to sum it all up, the well-quasi-order, that's our unseen connection. It's this beautiful mathematical rule that prevents infinite, incomparable chaos. We see it in action in huge results like Higman's lemma and Kruskal's tree theorem. And it's the secret sauce that makes automated verification and termination proofs possible, allowing us to build more reliable and trustworthy systems. And honestly, that's what's so cool about all this. The WQO was a pattern just hiding there in plain sight. It really makes you wonder, right? What other fundamental patterns are out there, quietly connecting all the complex systems around us, just waiting for us to find them?